So far, as you've just heard, my name's Nathan, and I've been using Go now since 2013. I made the switch back then from Java and have frankly never looked back. I then played a part in the team adoption of Go as our main development language, where I work at Turnitin. And we're an edtech company specializing in plagiarism detection and assisting students with the writing process. So in order for us to detect potential cases of plagiarism or identify original source material in a student submission, we need to have a large store of papers, journals, books, web pages to match against. I work on the team that's responsible for that ingestion and report generation process. In software at the moment, it seems like monolith is something of a dirty word. If you happen to mention, I'm working on a monolith app, the response varies from pity, the kind of, oh, I'm so sorry, maybe you can work on something cool soon, to one of expectation, the kind of, oh, you're moving away from that to microservices though, aren't you? And yeah, there's lots of advice that is move from the monolith. Don't start with a monolith, break everything up. And in cases like web applications with large amounts of traffic and clearly defined areas of responsibility that can be composed in a variety of ways by consumers, this may be good advice, but there are still applications that are not like that. And I believe that our software solutions can easily become overly fragmented and the boundaries of clear concern lost in unwritten interdependence. And I've seen this played out over a number of years in a variety of domains and languages. Architectures that confuse the difference between orthogonality and fragmentation lead to problems for both the code and the engineers. And we need to consider the benefits of reducing, simplifying, and minimizing our architectures with a less is more mentality. But before we go any further, we should define monolith. The design philosophy is that the application is responsible not just for a particular task, but can perform every step needed to complete a particular function. To put it another way, a monolithic application is one which takes care of an entire process from end to end, handling each step in that workflow. Drawing on recent experience of migrating a largely fragmented architecture, I will show that Go provides the constructs to reduce the number of services and moving parts you need, while still maintaining clear separation of concerns. So what follows next is a true story, a recent story, and one that bucks the trend. Now, before we dive into the story of why and how we built a monolith to solve this problem, there are a couple of key terms that need to be defined. First of all, a provider refers to any organization, publisher, or group of publishers that supplies us with content items. It's just a source of our items. And an item is that actual piece of content, be it a journal article or a chapter in a book, along with any metadata such as title, author, and journal name. We ingest that content and then it's available for matching against. So with those terms in mind, here is the legacy stack. And this is the basic architecture diagram. And it's also our essential problem statement. This was responsible for ingesting non-public content, so where we have a partnership with the content owner. And despite the complexity of this diagram, this is the basic overview. There's so much more to this process, more sources, more apps, more data stores than I could realistically show on one slide. As a quick rundown here, though, the red and purple boxes at the top, those are the remote disparate collections of vaguely related data that we need to ingest. And each of the rectangles then represents an application, a script, or a cron in the process of retrieving, parsing, and indexing that data. And each stage in the process is then either started manually, run on a cron, or is supposedly an HA long-running app. So as you can see from this, it's hard to hold even this high-level abstraction in your head, especially as these rectangles, there were typically more than one per data source. The architecture and data flow of each of those apps is another level of detail that we can't possibly memorize. I've not even named the apps on this diagram, as there are too many names and they just lead to more confusion. I once gave a 30-minute talk on just this slide to my teammates to convey the structure of this basic workflow. Now, you're all spared that today. We're not going to be doing that, thankfully. But one word for this architecture is fragmented. Lots of different apps and services doing lots of different things. It's fragmented. This is the same level overview of the new system. Much simpler, much easier to reason about. As you can see, we still have all the data sources. And we did work with some providers a little to simplify some of that, but we still track that information and we still index the content. For example, we moved one provider from giving us 4 spreadsheets via email plus multiple XML files via FTP to one XML feed retrieved with a standard protocol. But yes, at present, we're still dealing with XML, even in this modern world. But we can easily display the data flow through this system. And most importantly now, that data flow is completely consistent for all our providers. And this is what makes it a monolith. This is a single application that defines and implements a complete workflow. We could have taken our previous architecture and built microservices for each component. This would have brought increased clarity for sure, but I don't think it would have been the right choice. It would have introduced extra complexities. So microservices are not a free lunch. If we just briefly consider the alternative a little further, we can see that using microservices for this pipeline would lead to that greater complexity. This alternative approach adds in more components, more technology to understand, and more layers to manage. The communication such an architecture would use, be it REST or gRPC, would have an increased latency when compared with simple function calls and channels. So under this alternative, we would be able to spread work out across a cluster, giving specific resource to certain parts of the pipeline. Now, that's a really nice sounding benefit, but it's not actually something we needed with this application. We don't actually need it to be HA, and we don't need horizontal scaling. So further, the drawback to this approach is more complex configuration, deployment, and testing. With the monolith approach, we can test the end-to-end very easily without the need to manage the communication between services. We can deploy the app in one go, ensuring all parts are consistent with one another. Configuration and tuning is done with only a YAML file and a restart. Now, these benefits for us in this context were worth pursuing. So data flow is a key consideration in choosing a monolith. In this case, the data has to make it all the way through the system. So breaking each component or stage out into its own microservice is possible, as we just saw. But if each step has to happen, and they have to happen in order, then the microservice approach doesn't really buy you any major advantage. Tracking data flow in one application is far simpler than it is in multiple systems. You have no need for distributed tracing or queuing systems, for example. So with a clear data flow, it's possible to have clear bounded concerns within the application. Beyond data flow, the other question to ask is, can any, or more importantly, does any component need to be run independently of the other components? Now for us, the answer is no, that's not needed. So the solution we settled on adds the clarity we needed along with architectural simplicity. We can, within this new architecture, see the internals of this application, where the data comes from, how it flows through the system, and what the end result is. We can hold this as a mental model of the whole system, so it's easier to explain to others. It makes way more sense. This is one application with a simple data flow. Now, around this data flow, we have a manager package that controls data flow. Each step is handled in its own Go routine, often launching a number of distinct worker routines. The interaction with the warehouse is handled via a small abstraction layer, keeping our database interactions in one package. So this combination of clear bounded concerns and a well-defined pipeline makes a monolith a good architectural choice that, with the power of Go, can still retain component orthogonality without introducing fragmentation. So while both microservices and monolith need to have clearly defined pipelines and well-focused areas of responsibilities, there are trade-offs in each choice. As you can see here, there were some key comparisons we looked at in making our choice. Picking up on a few of these, we decided the use of channels, as we'll see, was the best way for us to define the pipeline. So we traded off distinct services and horizontal scaling for clarity of data flow and in-app scalability. I think the biggest drawback of this choice is that we have to have our app all off or all on. And there have been one or two times when being able to keep one part running would have been useful. However, this has been a small price to pay for the simplicity we've gained. Simplicity that comes in the code, in the testing, and in the configuration and deployment. The final main benefit for us in this application is that Go's package structure has made sharing code within the monolith very simple, certainly easier than having to deal with dependencies on shared repos in multiple distinct microservice repos. So, having defined our problem, outlined the solution we chose, and detailed why, here is what made it all possible. Key concepts from Go within the architecture that allow us to deliver a cohesive application whilst retaining clear boundaries are interfaces, Go routines, and channels. And I'm going to look at each in turn and demonstrate how they helped. So interfaces are a key part of Go, and understanding them clearly is vital to writing good Go applications. So what follows is how we leverage their power rather than an explanation of how they work. So within the ingest of content, there are numerous types of provider. each with slightly different approaches to how we retrieve the data, how they format the data, and what data they provide. There are as many data standards and delivery mechanisms as there are publishers. That's why our old architecture had so many files, scripts, and apps. We had one of those for each of them, kind of one for every standard. However, the key part of the data pipeline remains true. We want to process that data consistently for all types of provider. And process is defined for us as being able to fetch and parse data and generate complete content items. So using a small single method interface allows us to handle all this very easily in code. A simple interface acts like a clear contract for this specific stage in the workflow. It provides us with guarantees on what is going to happen within this step. Within this interface, we can define the manager struct to use this. So a manager needs to know about each of the processes that are in use, but by using the interface type, we're making certain guarantees about what processing will look like. This allows us to simply call process, making for cleaner code. We can still support the plethora of data standards, the multitude of retrieval mechanisms, but we can do it cleanly in one app. Process details are distinct, but we have no fragmentation. When processing needs to happen, we know there's a process method available because the member on manager is of the interface type. We know then that it will always populate the item channel and so satisfy our internal contract for data flow. Using this interface allows us to craft a manager that has what it needs without needing to know about implementations. In this particular case, it then simplifies or dries up any error handling we would want to do. This keeps our boundary of concern. The processors are responsible for the processing, and the manager simply knows to invoke that part of the pipeline. We'll compare this with the previous architecture, under which we had distinct apps, services, and scripts for different content providers. We still have correctly scoped responsibility and can still have distinct providers being processed simultaneously, but we do not have to manage and maintain distinct code bases or distinct running processes. If we'd done this with microservices, I think we would have had a processor service that worked with a similar interface, but the communication between stages would have become more complex than a simple set of Go routines using a shared channel. And we also use interfaces as parameters to functions. Here we have an interface definition that defines the required consistent behavior for parsing delimited files and XLSX files. Having this interface enables us to keep such processing grouped together in the right spot in accordance with our definitions of provider types. So we want to handle all our so-called independent data providers under one processor, and typically the only difference is the format of the metadata they provide, XLSX or CSV. So having an interface to handle the behavior allows for simpler handling of the data, and it means we don't need to fragment our independent providers as we once did. So if you recall all the purple boxes of the basic architecture, each data source being one provider also meant each data source had a custom script or application or even set of applications to process it. Here, as we'll see, we don't need that fragmentation. So this is it in use. The parse function, which is trimmed down to fit here, takes a spreadsheet type. Depending on the actual type of the metadata we're dealing with, we get the correct implementation, but it is of that spreadsheet interface type. This means that parse is focused on just creating content items. It has clear focus. The implementations of the interface take care of the file-specific needs of extracting the data from that format. So clear bounded concerns, orthogonality without fragmentation. Now, injection is another great use of interfaces that have helped us keep the application clear and well structured. Processors need to fetch from third-party servers, and we want a standard definition of fetching so that timeouts are correctly defined and headers we use are consistent between processes. So injecting a fetcher into the processor simplifies that. It also means that processor, which needs to fetch the data, doesn't have to know how to fetch. As the processor is really concerned with processing data, having a fetcher on it ensures a clear boundary and helps us maintain clean code. Injection also has benefits in unit testing. We don't want to hit third-party servers while testing, and in all cases, we're yet to find a provider with a test server we can actually hit. So injection comes in really handy. When testing a processor, we can create and inject a mock fetcher into the processor. As we injected the mock into the object under test, we can reliably predict the results. This means that the testing focuses on what happens with the data and not the retrieval of the data or the performance of a server beyond our control. We can even inject a mock fetcher that returns bad results to ensure we handle those correctly. Like at this point, we can make bad results absolutely anything, or even mock a failing server. Having knowledge of your domain will lead to clearer testing and make it more likely you catch edge cases. Injection like this allows you to handle those edge cases easily. It also allows for simple test-driven development even when there would be external dependencies. Now, if you do want to exercise actual fetching, then HTTP test is an excellent package from the standard library. I'd recommend it. And if you haven't used it, I'd be happy to show you how it works. Just reach out to me on Slack or Twitter. My handle was at the start there on my first slide. But as a little aside here, there are a couple of packages we found very helpful for unit testing. As I said, the HTTP test one from the standard library for setting up test servers. Then there's HTTP mock from my good friend Dan Kinder. Takes that idea a little further. It's kind of really easy to use and the test results are really elegant. And then there's Testify, which covers more than just mocking servers, but the whole mock interface here is really worth exploring, regardless of your architectural pattern. So it's just a quick aside, sharing some helpful packages with you. If you want to see some more examples, then reach out to me and I'll happily find a way to demonstrate them to you. So using interfaces in this context provided us with a simple way to separate concerns and yet implement a cohesive application. No fragmentation and no spaghetti code. Within the application, the various interfaces we have define certain behaviors of components. And while that doesn't prevent you doing stupid stuff in the actual code, it does help you maintain focus by clearly outlining purpose, which is good for the developer and the application. Interfaces are superb for injection, allowing you to both simplify production code, as the processor example hopefully showed, and keep focus on your testing. Being able to mock responses is useful when dealing with third-party servers or other external dependencies. So, wrong way. Oh, wrong way again. This one, sorry about that. So, routines next. It's hard to talk about Go routines without channels, but the two features sit so well together and can be composed in a variety of ways to deliver concurrent systems. Like having written concurrent applications in a variety of languages, I can honestly say that Go is by far the nicest. I'm sure you'll agree. Now, when thinking about parallelizing an application, stop and think about the data flow. Draw it out on paper, kind of attempt to visualize it. Pre-optimization is a no-no generally, and definitely in the use of Go routines. So concurrency is complex. When needed, it's superb, but when it's not needed, or if you aren't sure, don't do it. So next up, some examples of how we replaced fragmented multi-instance systems with balanced use of Go routines. Now, worker pools are a particularly useful concept when the same tasks need to be run several times. Great for fetching data from distinct connections at the same time. Great for running multiple different processes at the same time. And having a worker pool self-contained keeps it easy to reason about. And you can kick off the enclosing function in a Go routine, making the whole thing non-blocking. So this function snippet defines a worker pool. And this function can be called in a Go routine, as I say, to make it non-blocking. The process provider function called here is where the manager struct takes advantage of the processor interface and can essentially call process, regardless of the provider type. Now, under our old system, this was handled by multiple running instances of an application, and keeping track of those meant an in-house management system. The fact that this function is called in a Go routine and is non-blocking means we can also start another worker pool for handling the items that processing providers generate. So using distinct worker pools, one to send on a channel and one to receive on a channel, means we have a clear and continuous data flow. Further, this idea also gives us easier control over how many workers there are, providing easy performance tuning. So under our previous architecture, we had numerous applications that we would spin up multiple instances of in order to increase performance. With this new architecture, we can simply add to the worker pool to get the same result. So early on in the release of this application, we were processing sort of 50 to 80 items per minute, but we needed to jump from that to being able to process 500 items per minute. And because of the architecture we have now, we were able to achieve this with just a config change. So we increased our worker pool size and took our performance to between 750 and 800 items per minute. And all of this without adding more app instances to a custom app manager, without needing to keep track of what instance was processing what data source. Also, as we had one app, we could tune each step in the process in the same config update. So not like having to tune several different apps and then coordinate the releases. Now, this particular experience proved that the monolith was a good choice for this app. So out-of-band processes are very good for those tasks that are ancillary to the main application. And using Go routines for these means that they don't impact on the main focus of the app, but you don't have to worry about deploying, configuring, or managing them. And this approach has meant we don't need separate apps for tidying up, which we did have previously. And this is also the building block for replacing all of our crons. So Go routines coupled with channels means no more crons for us, but more on that later. So as an example, within our application, we download data from remote sources and we keep the original file on disk for up to 6 months. But that data does need to be cleaned up. We do need to delete it. We have a function, clear old items, that does that deletion. Details don't fit on the slide, but essentially it's an infinite loop controlled by a select, and more on that under channels. The point here is that it has no impact on the main function of the application. Small Go routines that happily run forever. No need for separate apps or services for these simple tasks. So our benefits are things like worker pools helping to parallelize various parts of the process, asynchronous processing of different stages of the pipeline, and a way to handle out-of-band processes within the application. So on to channels next. Now, moving data between stages used to be one app to read from the source and write to the database, then one app to read from the database, write back to the database and send to the index buffer, and then a third app to read from the index buffer, write to the index, and update the database. And now we have one app that reads from source, writes to the index, and writes to the database. And a key part of this is channels. So we replaced a host of poorly communicating systems with one monolithic app that communicates internally across channels. So the use of 2 channels along with Go routines defines our data pipeline very clearly for us. A clearly defined data flow or pipeline is essential in any architecture. And what we found is that Go enables us to define this very clearly and robustly, even within a monolithic application. We have a clear pipeline with no spaghetti code and no overreaching dependence. Now, within our application, as I've said, we have this central component manager. It's kind of the controlling brains of the process. And this component defines these channels. It sends and receives data on the channels and passes the channels to the processors. So the manager, responsible for controlling the entire data pipeline, defines both channels. So on instantiation, we create those and then pass them to the functions that need to send or receive on those channels. And this code snippet shows how we've used Go routines to define the data pipeline. The channels defined here are the conduits through which the data flows, sharing memory by communicating. And using Go routines for the first part of the data pipeline and a blocking call for the final stage means we can be continually processing data all the way through to that final stage. Having the final stage be a blocking call, it's kind of continually ranging over the item channel, means that this is a long-running app, and we can easily shut down by closing out channels within the pipeline, allowing them to drain and for the blocking call to return. Now, most importantly for us, this full flow is defined in 5 lines of actual code. So you can see the flow at a glance and understand where the data is going to move. This was an important consideration in choosing this architectural style. It's clear and easy to reason about. So the provider channel is populated with details of providers we need to process. There's a function continually reading the next set from the database and sending them on the channel. And this snippet shows that the continual range over the provider channel. Some details left off for brevity, but having the centralized channel means that the pipeline, which sends and receives on this channel, is clear and obvious. And we can see here that we're simply receiving the next provider on the channel and calling process provider, moving it on to the next step in the data flow. So recall then that the processor interface defines a process method that takes a channel as one of its parameters. As we hit process provider, we'll call the relevant concrete implementation of this interface. This then generates the item records from the provider source and sends them on the shared item channel, moving the next piece of data along the pipeline. And we're continually working through the pipeline, but with interfaces, Go routines, and channels, this remains clear and well bounded. Now, with each processor sending, with each processor sending data on the same shared item channel, we can easily centralize the next step in the flow within Manager. So this dispatch item method controls a worker pool where each worker ranges over the item chain, calling process item. That's the final step in the pipeline. So we have data moving through the pipeline. We're then processing the items from a variety of sources in a completely consistent manner without really needing to know the details of the provider at the point of handling the items. Well, this combination of channel and Go routines is really where we got our simple in-app scalability from. Comparing this to distinct apps to handle overlapping parts of the pipeline, and we can see that our previous architecture lacked this consistency. Unwritten rules were lost and not obeyed. Now, if this were completed in microservices, there would either be a queuing system in place, not unlike we had previously, though hopefully not in MySQL, or there'd be HTTP calls, and neither of those are as simple or effective as the channels-based communication we now have. It's also conceivable that under a microservices approach, we could have had multiple services writing data to the database, and that could lead to data confusion as boundaries of responsibility get blurred. Or it would lead to latency as we introduce a distinct service to handle database interactions. So moving on from data flow, channels have numerous other uses, not least of which is as a semaphore. We have a requirement from one of our data providers to not make more than 10 simultaneous initial fetches. Now, handling this in Go is a breeze. Under the old architecture, we got around this issue with manually starting a distinct application to fetch this data. Then a separate process was started to read and parse the data, and we were making only one fetch at a time, regardless of it being initial or not. Now, when we create the new processor in Manager, we instantiate a buffered channel. It's easy for us to determine if a specific fetch is deemed initial, and if it is, we attempt to send an empty struct on the initial fetches chain prior to making the fetch. That send is a blocking call, so if it works, we had space for the fetch, and if it didn't, it will block until there is a slot available. And once the initial fetch is done, we receive on the channel, freeing up the slot. So using the channel as a semaphore, we can obey the restriction without needing to rely on manual processes and without needing distinct applications. Handling this limitation is part of the concept of processing that data, and so it belongs in the processor and not in a distinct application. Now, the Cron replacement, and I hinted at this a little when I talked about out-of-band processing and Go routines. Under our old architecture, this was a distinct set of applications or scripts which were run with cron jobs. And the biggest issue here was forgetting they were running or having them be misconfigured or sometimes just forgetting to set them up at all. Now, using the select for pattern and the Go time.after channel, we can easily ensure that the processes like clear old items only happen every fixed duration. Now, this is not quite the same as a cron, I admit. Cron is fixed time each day, but in this case, the trade-off is worth it. Having separate applications for this also meant distinct code for managing database connections, giving us duplication across apps and in different languages. By keeping the code in one app, it's naturally in the same language, but it's deployed with the app, it's turned off with the app. Database management is in one place. And by using the distinct Go routines too, we keep the process contained, yet avoid fragmentation. So using channels in a variety of ways has helped us to model in code the data flow of the application. And this was initially whiteboarded out and then translated to code. And that translation was simple. There's no reliance on external services or systems and no use of data stores for communication and pipeline management. This makes understanding the data movement really easy. And when asked then to restrict the number of requests we were making, a buffered channel becomes a semaphore. This shows how simple that is, and also that channels and Go routines can play separately from each other. Now, along with the out-of-band processes we saw before, the use of select and time.after means no more crons. And this removed a significant pain point from the previous architecture. So recall the architecture we started with. With Go, using interfaces, Go routines, and channels, we've reduced the fragmentation. Each of those fragmented parts of the architecture has gone away. We have a single cohesive whole. We now have one application that is well-defined and clearly understood. It handles the full data process from start to finish. We've removed the fragmentation we once had and still maintained correct focus of concern and orthogonality. All the distinct applications replaced with a unified monolith that allows us to control data flow accurately and deterministically, giving us clear, simple insight into the application and providing a far better solution to the original problem. So the monolith is a useful architecture. It remains useful, but like any architecture, it does need to be used in the right place, and it does need to be used with care. There are certain lessons that apply to microservices and monoliths. Know your data flow, define your boundaries of concern. And once you have the data flow and the boundary of concern, you can define a controller or manager that will handle running the pipeline and ensure that data is moved as required and that the components are used correctly. This gives you a certain level of assurance that the data you care about is moving through the full system in a timely manner. When you know that the data you're processing has to make it all the way through distinct stages in a timely and deterministic manner, you have a good fit for a monolith. The issue with a microservice for this sort of application is that you introduce a number of extra complexities: inter-service communication, service availability, and distributed tracing, being a few of the concerns and complexities that just don't exist under the monolith approach. So Go provides us then with a number of primitives that are very useful in the monolith. And hopefully this talk has shown that the monolith is not to be feared, pitied, or shunned, but used wisely, and that it can be an architecture with retained relevance. So thank you for your time. I'm not sure if I've got time for any questions now, but you can reach out on Twitter or Slack. As my handle was at the start, it's @nathj07, and I'm always happy to help. And I'm always happy to learn from your take on this too. So thank you very much.
Thank you so much, Nathan. That was great, and that was very informative. And it's good to know that microservices is not always the answer. As you said, there is no time for questions, but people can definitely find you on Twitter. And if somebody didn't catch the handle, just follow GoRemoteFest on Twitter, and then your talk is being tweeted and your handle is being tagged.